Yeah. Yeah. Is it visible to you? All of you, the shared screen?
The whole.
Yes, sir.
Yeah. Now,
Yes, sir.
yeah, we just start our class by just repeating what we have learned in the earlier class quickly, and we'll go. We have seen in the earlier class what is induced absorption. We have two levels, call it as ground state and excited state. In general, the ground state is more preferable state because it's a stable state. Hence, under any normal conditions, thermal equilibrium conditions, there are more number of atoms in the ground state. Therefore, N1 is greater than the number of atoms in the excited state N2. But if you supply some external energy equal to the difference between the two energy levels, atoms will go. And this process we call it as induced absorption. Okay, when I supply some energy to this. So therefore, you can see that we have supplied some energy to this and they have gone it. Therefore, we have seen that the rate of transition, okay, this will not go here because the supplied energy only this, and therefore it cannot go here because the supplied energy is between these two levels only. Here this level is not okay. Suppose say N3 are there, maybe, okay, or we say this is N3, okay, and for E3 level it is not possible because we have not supplied that much of energy. Therefore, we have seen that the rate of transition, okay, D1 2, that means from one level to second level is proportional to B1 to N1. That means it depends on the energy we have supplied. This is rho mu, what we have called it as the energy per unit volume, and is proportional to the more the number of atoms are there in N1, more is the number that are going away. And we have seen this with B12 as the Einstein coefficient of induced absorption. Now we look at spontaneous emission, where we are supposed that atoms are already there in the excited state, but they cannot stay longer time here because it's an unstable state for the system. Without supply of energy, they'll come down by themselves. And under such case, the lifetime, that means the average life in an atom spans in excited state is called lifetime. That may be around 10 to the power minus 8. If you take hydrogen, it is 10 to the power minus 9 seconds or so. Therefore, immediately they fall down without requirement of any external energy, giving rise to a downward transition and an emission of energy h nu. Therefore, okay, one atom will come, will get a wave. Another atom after some time will form, and other atoms will come, but they'll cut at different times. Therefore, the waves are not coherent. They'll get at different times. That is the spontaneous emission. But to get laser, okay, or if you take the spontaneous emission, the rate of transition D21, we wrote it as D21. That means from level 2 to level 1 is directly proportional to N2 only, the number of atoms that are there in the excited state, because we are not supplying any additional energy. It is only the energy which is coming out is this. Okay. So therefore, A21 is called Einstein coefficient of spontaneous emission. We have seen it. And we'll go for stimulated emission, which is most important for us. Okay. Now we have here level 1, okay, ground state, and we have another level somewhere here, N2. And suppose if I give energy, they go quickly to the third level, E3, but its lifetime is very, very small. Therefore, they fall very, very quickly to N2. See how fastly they're coming and falling. But if you see this level where you choose here, okay, if you choose there, you can find it that, okay, here the energy level is 10 to the power minus 8 seconds. Okay, thereby within no time they will come to N2 level very quickly. But here there is no radiation coming out when the atoms are coming from E3 to E2 level. This I call it as E2 level. And I call this as E1 level, having N1 number. We have gone, taken it up, and they have gone here. So here this is called radiation less transition. Radiation less Means no radiation will come out, but this energy will be dissipated in the form of heat, or it will be given to the lattice. So radiationless transition we call it as. No radiation will come or no light will be emitted, but the energy is wasted in the form of heat. So that's why such radiation called radiationless transitions are, we also call it as non-radiative transitions. Non-radiative transition. So during this transition is nothing but moving from one energy level to another energy level. They are moving from here to here. Very quickly they are coming because the lifetime is small. But if you go to level 2 N2, okay, this N2 is the number of atoms in the higher energy level E2. But E2 is having, okay, more lifetime 10 to the power minus 6 seconds. Suppose say I make this as 10 to the power minus 9 seconds. Then if you come to E2, E2 is 1000 times more life than E3 because it's a nanoseconds. This is microseconds. Therefore, in some atomic systems, there will be some energy states which are having higher lifetime. This is higher lifetime state, higher lifetime. So therefore, the energy levels having higher lifetime, they are called as metastable states. Einstein postulates that some atoms will provide you energy levels with more lifetime than normal energy levels. Normal energy levels may be varying 10 to the power minus, okay, 9 to minus 8 seconds. Therefore, they don't spend much time. They will quickly fall down to another state. If this state is not there, then they'll quickly fall to the ground state. But if you are able to give by providing some energy states having longer lifetime, which we call it as metastable states. Therefore, the atoms will stay here. More of the atoms will be staying here. Now, if you see that, and if you compare E1 and E2, E1 is having only 2 atoms here, if you see it. Okay, that is N1 is only two atoms are there. If you see here 1, 2, 3, 4, 5, 6 are there. Now N2 is 6 atoms are there. That means the population or the number of atoms in the higher energy levels here, okay, E2, that is N2, is higher than the number of atoms in the lower energy level, which is not happen generally because it is not a stable state. In most of the cases, we have under thermal equilibrium more number of atoms in E1 and therefore N1 is always greater. But here we have got a situation where N2, the number of atoms greater than, okay, in the E2 is greater than number of atoms in the, okay, lower energy state, if you see it. Therefore, here there are two important points you have to note down. One point is that if you have a metastable state which is having larger time, therefore atoms will come and settle here. Thereby, I will get a time to throw all these atoms simultaneously down to this. Therefore, all atoms will fall at the same time. Unlike spontaneous emission. Spontaneously, different atoms are falling at different times, and therefore they are giving waves at different times. Therefore, they are not coherent. If I make all the atoms to take downward transition, then all they will release waves which are in phase with each other. Otherwise, I'll make them the waves to be in phase with each other. Then the requirement is that I should have some time to make the atoms to take a downward transition. That means we need a higher energy level, higher than ground state, which will have longer lifetime. So the energy level that is having longer lifetime is called as metastable state. So understood? What is the metastable state? Metastable state is an energy level the atomic energy level which is having longer lifetime than the normal state. And such state is important so that I can keep the atoms there for some time so that the atoms will be accumulated at that energy level. And if more the atoms are accumulated, when they fall, they will give you more number of photons down. And therefore, the first one is metastable state. The second one is population is more in higher energy level E2 than the lower energy level, which is not possible under equilibrium positions. So the condition of having more number of atoms in excited level E2 than E1 is called as population inversion. Population inversion. Population inversion means that the number of atoms are called population, just like the population of a given country or a population of a city, if you take it. So the population in N1 is less because I have only 2, but in excited state we have more, that is 6. Hence the population is more. That means general condition of thermal equilibrium is inverted. Is inverted means we have more number of atoms in the excited state than the ground state. That condition is called population inversion. So Einstein postulated that if you have a population inversion, then you will get a stimulated emission if you provide a matching photon and if you have a metastable state. Metastable state is a state energy level having longer lifetime. So these two are requirements for getting stimulated emission. Therefore, the stimulated emission, if you see it, okay, they will fall down here. If you give energy, I'm supplying energy, this rho mu, okay, and therefore this atom is going and coming here. What is happening? You see this. What I'm doing is here, okay, this is coming. The photon is okay. I have given a photon. This photon moves in the atomic system. Then I put a mirror here. It gets back. This is the mirror. Okay. And therefore I have 2 photons. If another atom is falling, this will be increasing. If you see it, the more the atom they are falling, all of them, I'll keep another mirror here. They get reflected back and forth between the 2 mirrors. And hence the number of photons between the 2 mirrors increases. And we have a coherent beam. And all atoms will fall from metastable state to ground state, giving you this coherent beam of it if you supply this matching photon, because now we have time to supply matching photon since this have more large number of lifetime. If they are there, I don't have a time to supply external photon because their lifetime is less. And therefore the rate of transition, we'll write it as, is proportional to the supplied energy, that is called rho mu, and also depends on the number of atoms here, which we call it as N2. Thereby I can write D21, which we call it as stimulated emission ST, is equal to B21, called as Einstein coefficient, okay, number of atoms in the air state. This is the incident energy density. These all we have seen it. But another important thing is that at thermal equilibrium, upward transitions must be equal to downward transitions. Means that I have E2 here and I have here E1. And there are N1 number of atoms here, N2 number of atoms are there. They are going up because of induced absorption. That is, okay, we call it as upward transition. But they are coming down by themselves without giving any external energy, which we call it as spontaneous. But if it is a metastable state, they are also falling by taking external photon, which we call it as stimulated emission. Therefore, induced absorption is upward transition. That's what we have written. must be equal to downward transitions. This is okay, spontaneous one, and this is stimulated one. Stimulated one. Therefore, if I send 100 atoms to top from the lower energy level, 100 atoms will fall down. 101 atoms will not fall. Or 78 will fall and some other will not be there. Some of them will fall down because of spontaneous emission. Some of them will fall down because of stimulated emission if you meet the requirements. That's why the upward transitions must be equal to downward transitions at equilibrium. So upward transition is only induced absorption, downward transitions are this. From this expression, I want to calculate what is energy density rho. If I take the other side, I will get like this. That is N2, okay, whatever I'm taking here. Okay, so N2 by N1, this is the condition. If I divide it by B12, I will get this condition. From this, you can use the general perception that A21 is induced absorption coefficient, B21, okay, this is also okay, is induced absorption, this is spontaneous emission, this is okay, stimulated emission coefficients, and thereby we will get rho is equal to this. And if you simplify this, okay, we have a Boltzmann law. Boltzmann law states that number of atoms in the higher energy level is varying something like this. Therefore, if I put N1 by N2 there, because here in the previous one we have here N1 by N2. So Boltzmann law states that number of atoms, okay, in the lower, if I want to write it, or in the higher energy level N2 is always a small fraction of N1. What small fraction? This is equal to E2 minus E1 with a negative sign by KT. If I inverse it, I'll get N1 by N2. So that's minus sign will go out. But E2 minus E1 is nothing but H nu. Therefore, only few of them, a fraction will be there at the higher energy level. If I substitute that ratio there, I will get this equation. By substituting in this the N1 by N2 value, I will get rho value this. If I substitute it further and simplify it, okay, according to Max Planck equation, this is the rho equation. If I equate them, I'll get these conditions. That means B12 is equal to B2 and this is equal to this. From this, the important conclusion is that if I have only two energy levels, I cannot get stimulated emission. Why? Because I have E2 and we want E1. To get stimulated emission, according to Einstein, two requirements has to be fulfilled. One, we should have a metastable state, which is a long-lived state. Suppose this is long-lived state, metastable state. Not stable, it is metastable. Okay, so metastable state it is. And then second is we should have more number of atoms, which is called population inversion, at the higher energy level than the lower energy level. That means N2 must be greater than N1. This is the requirements. But if I take two energy levels only, suppose say I have sent 6 atoms up. If three of them, suppose that they fall down. Okay, if 3 of them they have fall down, what happens is that I have at the top only 3 of them will be there. Then N1 equal to N2. So I never get N2 greater than N1 if I take two energy states. Thereby, two energy level systems never will give you a lasing action or a stimulated emission. Therefore, two-level systems, two-level means two-level atomic energy level systems cannot produce laser. That is what we can get from here. That is the most important aspect you have to learn it. So, but what is the difference between the spontaneous emission and stimulated emission? But what more important is that, okay, the emission, spontaneous emission takes place without external energy, without help of any external incident photon, or no external energy is required. No external photon is required. But for stimulated emission, we have to give, okay, an incident photon, and that incident photon will have energy equal to E2 minus E1. Therefore, incident photon triggers other atoms in the higher energy level to come down, and this photon we call it as this external photon, which we are calling, we are sending, okay, or we are giving, is called matching photon. This is the important. Then most another important thing is that, okay, the emitted radiation is polychromatic, not monochromatic. But whereas in stimulated emission, okay, a radiation emitted is chromatic, consisting of single wavelength. We say is a right monochromatic, not chromatic, monochromatic, I write monochromatic. So I'll get only one. Radiation emitted is monochromatic, but spontaneous is not monochromatic. And actually this is proposed by Bohr and this is proposed by Einstein. And then another important thing is that, okay, it is less intense, but it is high intense. High intense. Then one more thing I have to add is in this is, okay, they are incoherent beam. We'll get incoherent. We will get an incoherent beam from this. I just erase this and right here. Okay, I'll get a incoherent emission so occurs in non-radiative process, but here, okay, emission is incoherent, means coherent beam cannot be observed. That means the spontaneous emission will not give you laser light, but here emission, whatever you are taking, okay, is coherent. You'll get coherent beam, means we'll get the waves that are maintaining a constant path difference or a fixed path difference between them. So these are the some distinction between spontaneous and stimulated emissions. Now we have already defined what is a metastable state. So metastable state, the average lifetime the atom spends in excited state is called lifetime. Tau we generally call it as. And ground state has infinity time. That means because it's a more stable state, the atom lives there only, and there will be no other state lower than that energy level for the atom to go down. Therefore, it will be there. Okay, and the lifetime of hydrogen is 10 to the power minus 7 seconds. Now, in some substances or some atomic systems, they will have excited energy levels, excited energy states we call it as excited energy states, only in certain atoms or only certain substances, for which the lifetime is greater than normal lifetime. Such long-lived states, we call them as metastable states. And metastable states are in the order of micro to milliseconds. Okay, in the order of micro to milliseconds. That means the lifetime when compared to ordinary energy levels, it is 1,000 times more or maybe 10,000 times more. And these systems play a very important role in the emission of a laser light by stimulated process. So we have now definition of metastable state. Metastable state is a long-lived energy state, a long-lived excited energy level, whose lifetime is more than the normal energy states. So we require a metastable state for getting stimulated emission because we require some time for us so that the atoms are there in a given energy level. If they immediately fall down, I don't find any time to supply external energy. That's why we require some time to push all the atoms in the excited state to down by supplying of external photon called a matching photon. That's why we require a metastable state for lasing action. Next, second is what we have defined already is population inversion. So if you take it here, I have more number of atoms here and less number of atoms here. Thereby, if atoms are falling by themselves, they'll give you, okay, all of them are falling. So that is previously the atoms are in the excited state, all of them. So therefore, I can say N1 in the ground state is having less population compared to excited state, which is having more number of atoms. So, okay, so this is N2, I call it as N2. This is E2. Therefore, N2 is greater than N1. But you should remember that under equilibrium, under thermal equilibrium, under normal conditions, there will be always more number of atoms in the ground state. More number of atoms I'm talking about in the ground state. Since ground state is more stable state or most stable state. If atoms will go to excited state, atom will become unstable and therefore immediately it tries to come to ground state by losing energy. Therefore, having more number of atoms in the excited state is something different from the thermal equilibrium state. And such state we call it as negative temperature state. Okay, which we have more number of atoms in the higher energy level, and this condition having more number of atoms in the excited state than the ground state, we call it as the population inversion condition. Population inversion means population is inverted. How it is inverted? Previously we have large number of atoms in the ground state. That is a normal condition. But we have made more number of atoms in the excited state so that they'll fall and give you a coherent beam of it. And that state of having more number of atoms in the excited state than the ground state is called population inversion, since population is inverted. Inverted means instead of having more number of atoms in general conditions in ground state, we have more number of atoms in the excited state. That state we call it as population inversion. So these are very, very important conditions for any lasing action. We'll see how we'll get this lasing action in a given scenario. So we will start this population. How do I get population inversion? How do I get population inversion means that how can I take atoms from ground state to excited state and see that there will be more number of atoms in the excited state. Then only I'll get a stimulated emission. For that, there are many methods. One of the method is optical pumping, electrical discharge, forward biasing, if it is a p-n junction diode, or chemical means or mechanical means. But we will discuss them soon in detail how to get population inversion. Now we will look at another important thing called pumping. The process of getting atoms in the excited state more in number is called pumping, because I have to pump the water from the ground level to excited level by using a motor. If I have a motor, suppose say the motor pumps water here and pumps this one to excited state or a tank. It pulls it in. So thereby what we require is that we have to pump the atoms into the excited state, just like a motor pumps the water from here ground level to the higher level waterfalls. That means to take the water from ground level to excited level, we have to have a certain external agency to make the water to go to the overhead tank. That's agency or the one which is taking water from ground level to higher energy level is motor. Similarly, in atomic energy levels also, if you have energy level E2 and if you have one E1 here, and if the atoms are there here, I have to pump them up. I have to take them up. How do I take them up? I have to give external energy. Okay, I am giving h nu is the external energy, whose energy is equal to E2 minus E1. So by external energy, this is we call it as external energy. That is a motor, that is a pump. Okay, external energy. If I give external energy, the atoms will be pumped up and this level will be depleted, and therefore after some time, okay, by giving external energy, I can make to have more number of atoms in the excited state than the ground state. So therefore, N2, if I say here, N1 will be larger compared to N1. So the process of taking atoms from the ground level or low energy level to higher energy level is called pumping. So pumping helps us to get population inversion. This helps to get population inversion. Population inversion. So which is necessary for having a lasing action or to get a laser light out of the system. Therefore, what we use important definition is pumping. Pumping is the process of number of atoms count, if you say it, ground state to higher state with the help of external energy is called pumping. So the number of atoms, that is the population count in the excited state, can be increased more than the number of atoms in the ground state by supplying external energy. So this process of rising atoms from ground state to higher energy level, we call it as pumping process. Therefore, we define three important terms in this. One is metastable state, a state having more number of atoms, more longer lifetime, and then population inversion, the process of having more having more number of atoms in the excited state than the ground state. And pumping is a process of taking the atoms from ground state to excited state to obtain population inversion is called pumping process. These three are important processes to get a lasing action or a laser light from a given system. So that's what for what we want, we have to see. That's what we call it as components of a laser. What are the three important components or three important parts of a laser? Okay, first, what I said is that you should have a population inversion, or we require some energy levels to get metastable states. But who will give all these? Atoms will give. And these atoms or group of atoms or aggregation atoms may be there in the form of a solid or in the form of a liquid or even in the form of a gas. Therefore, a material, having some atoms, molecules, ions, they provide the energy levels. Therefore, the energy levels that are required to have a population inversion and to get a stimulated emission is important. Therefore, we say that the atomic energy levels are molecular energy levels that provide laser transition, and that substance made by atoms or molecules or ions is called an active medium. So active medium is a one first component of laser. Active medium is nothing but it is collection of active medium is a collection of a large number of atoms if it is atomic crystal, or molecule if it is a molecular crystal, okay, or ions if it is an ionic crystal. So it's a collection of large number of, okay, atomic, molecular or ions, collection of ion of a, okay, given substance. Why substance? Because this substance should have metastable states. So that collection of large number of atoms given substance, either in the form of a solid or a liquid or a gas. Because we know that solid, liquid, gases are aggregation of atoms, collection of atoms. If they are very close to each other, we have a solid. If they are little far apart, we have liquids. If they're too far away from each other, we call it as gas. Therefore, active medium may be a solid, liquid, or gas. Anything you can take it. Okay. So any one of these may be possible. Hence, that is called active medium. So first component of laser is that we must have a medium. Medium consists of atoms, molecules, ions. These atoms, molecules, ions will provide you metastable state. In the metastable state, we try to get population inversion by means of pumping. Therefore, first one is active medium. Active medium is a collection of large number of, okay, atomic, molecular, or atoms, you can say, not instead of atomic, we say atoms, molecules, you can say, or ions of a given substance, either in the form of a solid or liquid. That we call it as the active medium. Then we now look about this active medium is generally, if you take it, is of two categories. One of the category in the we say the active medium is now divided into two parts. So one we call it as host, the other is called active centers. Host means that, okay, host will be some substance, maybe I'm taking a solid, we have some atoms here, and these atoms we call it as host. But these atoms or atomic crystal may not be able to provide active centers. That means may not be able to give the what we call it as metastable states or metastable energy levels. Therefore, what I do here is that I dope some other element in the given crystal, something like this, some other atoms. These atoms will have higher lifetime, means that they provide metastable states. So these atoms which are providing metastable states are now responsible for giving, okay, the stimulated emission and lasing action. Therefore, we say these atoms as active centers. But why I can take directly active centers, you may ask? No, you cannot take. I should have some material. In that material, I have to imbibe or I have to dope some certain other atoms. This original one is now holding the impurities. Therefore, we call it as a host. Host holds the impurity atoms, and those impurity atoms we call it as active centers. So the first component of laser is active medium. Now the second medium, okay, second part of it we call it as pumping source. A pumping source is one which helps us to get a population inversion. So this is the first one. Second one is this. Okay, so population inversion to get means that population inversion is nothing but to take the atoms from the ground level to excited level and see that there will be more number of atoms in the excited level E2 called N2 than the number of atoms in the ground state. So that is important. And that process by which you are making the atoms to go to higher energy level, we call it as pumping. The process is called pumping, and we call it the source which is pumping is pumping source. That can be achieved by taking a light to fall on the active medium. Therefore, incident light energy is absorbed by the active medium and atoms will go to higher energy state. So that N2 will become N2. Or you can apply some forward bias in a p-n junction diode. Therefore, the conduction band will have more number of electrons, valence band will have more number of holes. That is also population inversion. Otherwise, apply some electric discharge, and thereby atoms will go from ground state to higher energy state. Thereby, the pumping can be have different types, as we have seen in the previous slide. Maybe optical, electrical, chemical, mechanical ways. All these will help us to get population inversion. That is a second important component of it. And a third important component is called resonating cavity. This is important. What is the resonating cavity? We have to see it. In some cases, we also may need cooling system because the energy released during the transitions is large, and sometimes it is in the form of heat also. Therefore, the active medium, which is a main resource for giving lasing action, will get heated, and thereby its efficiency or performance falls down. To make the active medium efficient, we have to keep it at lower temperature by using a cooling system. But what is the resonating cavity? What we have to see it. I told you in the earlier classes that laser is a resonator. That means if I have E2 level here, if I have E1 level here, I will give you a photon h nu, which is called it as matching photon. If I give matching photon, what happens is this: if atoms are there here, this atom, this photon moves in the system, but this will have h nu equal to E2 minus E1. If atom falls here also, it will have same frequency h nu is equal to E2 minus E1. Therefore, this photon excites the atom in E2. You come down as I'm moving. If this you also come down, then you will emit same frequency as that of mine, that is incident photon. Therefore, both will have same frequency. Hence, the incident photon moves in the system like this, and during that process excites or stimulates one of the atom in the excited state to come down because they have same frequency and they are in resonance. Therefore, there will be two photons moving in the system like this. And I have two different photons. One is the supplied photon, other photon is because of the stimulated emission, it will come down, and because of resonance, another photon will come, is appearing since the atom is falling down. Okay, therefore, to increase the number of more photons, I keep here a mirror, perfect mirror, and these photons will fall and get reflected back. They will come back. While coming, what will happen is that these two take another two atoms to come down, and thereby I'll keep another mirror here, and they shuttle between these two and increases the intensity. That is what we call it as a resonating column. Okay, so resonating column is the distance between or the space between two mirrors or two polished ends, which will give you amplification of photons, emitted photons. So this we will see in a figure format. Therefore, you can easily understand the components of a laser. These are the components of the laser. What we want? We want a medium. This is the medium. What are the medium? This is the medium I'm taking. So I take here the medium. So this is the medium. So this medium will provide you the energy levels E1, E2, okay, having the population N1, N2. This medium we call it as active medium. Why we are calling active medium? Because it provides required energy states. If you don't have a medium, you don't have energy states. Therefore, we call this as an active medium, which consisting of host and gas. So therefore I have this. So I'm pumping the atoms from the ground state to higher energy state by using external source. We have external source that is called pumping. If I pump them, atoms will move from lower energy level to higher energy level. But this higher energy level which I take here is having a lifetime of 10 to the power minus 9 seconds. Therefore, whatever I pump the atoms to E2, they seem okay very fastly, that is fast decay, non-radiative means no radiation will come out of it, will be coming to E3 level. So therefore, I have population inversion, means that when compared to E1, that is ground state, we have more number of atoms in the excited state E3. That's what we call it as metastable state. Metastable state will have longer lifetime. So we have metastable state. And we have more number of atoms in the excited state than the lower energy state. When I compare between E3 and E4, E4 is excited state but lower than E3. Therefore, I can have the population inversion between any two energy levels. So here also less, here I have only one, but here I have 7 atoms. Therefore, this system, whatever you take it, we call it as the population inversion between E3 and E4. Once the population inversion is there, the atom tries to fall down. This is the population inversion state. This entire one is population inversion state between E3 and E4. And thereby an atom falls down. It is falling down, something like this, and gives you a laser light. Therefore, here I keep a mirror. They'll get back. That means initially only one photon is moving and they'll come here. I put another mirror here, they get back. Okay, so therefore we will get lasing action. So to understand this, what actually happening within this, I will tell you something like this. Suppose say I take here only 2 levels. Okay, for our example, I am taking E3 here and I am taking here E4. And here the number is large. More number of atoms are there, population inversion. Here I have only less number of atoms, 1. Therefore, I will give you a matching photon h nu from outside. And this atom, this I'll keep here in the, okay, the entire medium will be kept between 2 mirrors, which we call it as resonating column. We actually keep it like this. Okay, and I'll keep a mirror here. I keep another mirror here. I keep this as M1 mirror. This I'll keep as M2 mirror. Then this photon moves and takes ask the another atom to come down. I have original photon which I have given moves like this. And while this is the original photon what I have given, the atom is coming down, therefore it releases an energy equal to h nu. So therefore I have 2 photons. Another photon exactly goes like this. 2 of them go here, gets reflected back by the mirror. Now I have 2 photons. These 2 photons ask 2 more atoms to come down because resonance is occurring. Hence I have 4 photons. 1 photon, original photon, other is the induced stimulated photon, and while reversing back they will give you 2 more photons and they touch here and they get reflected back, and these 4 photons will give you make the 4 more atoms to come down. Therefore I have 8 photons that are coming here. Thereby 1 atom which is for okay, one photon which I have given, one atom, one photon which I have circulated, when it's moving between the mirrors, it will get reflected back and forth. For each time, it doubles the photons. One original photon, one atom has fallen. Falling atom gives you another photon, two photons. And these two photons get reflected and makes two more atoms to come down. Therefore, I have 1, 2, 3, 4 photons. When these 4 photons are going back, by taking a reflection at M1, it gives you 8 photons because the 4 photons ask 4 more atoms to come down. And this will become 8. And they goes here, comes back. Again, 8 will become 16. And 16 will become 32. This is a cumulative process. Thereby, the number of photons will be increasing enormously. Hence, we say they get multiplied. Multiplied means that the number of photons are increased in progression. Thereby, the intensity of the light also increases. That means light is get amplified. But the entire light is moving between M1 and M2. But if you want to use that light, it has to come out. Then I have output light. Therefore, I will make this as okay, less transparent, maybe 90% transparent, okay, and I make this cell 100% polished. That means if it is 100% polished, the light cannot transmit, only it can reflect it. It's 100% reflection. But if I say 90%, then after some time, when the number of to and fro motion or to and fro journey of these photons between the two mirrors goes on increasing, the intensity of the emitted photons also increases. Then this 90% or partially reflecting mirror cannot hold that much of intensity, therefore it leaked out from this mirror and you can see laser light coming out of it. This process is called lasing action or lasing process, or lasing, we call it as lasing. So lasing will happen like this. So this is, now you see, this is the active medium kept between two mirrors, and this, okay, the photons are going and coming back, and that space we call it as resonating cavity. And this is L, distance is L, and this is fully reflecting mirror 100%. Only whenever light falls, it get reflected back only, that's all. But it is partially reflecting, okay, the light will leak out after some time. This is the pumping energy externally we are giving, and that will be taken by active medium, and hosts will take the guests, which we call as active centers. By pumping energy, active centers will go to metastable state and a population inversion is created. And once the population inversion is created, if you supply a matching photon and it goes like this and gets its here and come back. For each return tip, it induces one photon. And the two photons, again, if you repeat, they induce two more photons. Therefore, one photon becomes 2, and 2 will become 4, 4 will become 8, 8 will become 16. Like this, photons will increase when they are moving through the active medium between the two mirrors. Hence, these mirrors are providing a resonance between the incident photon and the excited atoms which are releasing another photon. And such process of multiplying photons between the resonating cavity is called lasing action. So the laser light will come from partially reflecting mirror, because this is 100% reflecting error. The light cannot leak out from here. The light will come out of this, and you can see laser light coming from this end. Hence, for a laser, we require active medium, pumping energy, resonating column. These three are minimum requirements to get a laser out of a given atomic or molecular ionic systems, maybe solid or maybe liquid or maybe gas. So I stop here. In the next class, we look at types of lasers. What are the different types of lasers? How to use them? Okay, so we look at this in the next class. What are the different types of lasers? Now, so this is a very important, simple concept to understand. So for lasing or to get laser, we require three important aspects. One is metastable state, population inversion to get, and also the active medium we want. Yeah. Yeah. Srivardhan, after a long time you are coming to the class. What happened?
Sir, some personal reason, sir.
Yeah. Are you okay now? Are you feeling
Yeah,
good?
okay, sir.
Yeah, good. But don't miss the classes, huh? Yeah,
Okay, sir.
students, I have one or two announcements for you. The first announcement is that the quiz will be conducted from the laser chapter and also from polarization, which we have completed. I will conduct it online through Moodles. Okay, on 13th. 13th February, we have Moodle quiz, and that will be conducted evening 5 o'clock. And I will give you only 10 questions. You have to answer 10 questions in 10 minutes. You will get 5 marks. Followed all of you? So we have a quiz on 13th, online quiz through Moodles. And we require, I'll give you second, this is second quiz. Okay. Second assignment, I will post it to you in the MS Teams quick, maybe very shortly, and you have to submit after writing